Hi all, welcome to this introduction on the DQ trace method, a new approach to seismic interpretation. Today we'll explore how this newer technique can help us better visualize and understand subsurface features in seismic data. That is particularly going to be useful in hydrocarbon exploration. The DQ trace method combines elements of AVO analysis and quantitative interpretation to provide clearer insights into our reservoir properties. In traditional seismic interpretation, we often struggle with limitations in data clarity, particularly when trying to identify hydrocarbons and characterize the reservoirs. Some of the common challenges we have include unclear layer boundaries, difficulty distinguishing fluid contents, and also some ambiguous thickness representations. And so the distance and quadrant attribute method addresses how these challenges can be addressed by how we process and display the seismic data. So I want to start with the basic workflow of the DQ trace method, and it's pretty straightforward. It involves just 4 steps. The first one is input data preparation using partial, near, and far stack traces. Second, we approximate the AVO attributes. In the third step, we do the quadrant optimization through phase rotation filtering. And then finally, we do the DQ trace calculation. So each of these steps is designed to enhance our ability to identify and characterize subsurface features, and I'm going to go through them next. So the foundation of the DQ trace method lies in its input data. So what we use is a near angle stack, so here from 0 to 10 degrees, and then also a far angle stack, so from 20 to 30 degrees in this case. So these specific angle ranges can be chosen to optimize the best signal to noise ratio while also maintaining sensitivity to both acoustic impedance changes in your reservoir and the fluid effects. The near stack primarily reflects the lithologic changes, while the far stack captures the fluid-related AVO effects. One of the crucial aspects in the DQ method is the concurrent phase angle analysis. And so here's kind of how it works. We start with a 0 phase trace, and then we apply multiple phase rotations. So shown in this example as plus 45 degrees, 90 degrees, and minus 45 degrees. And then based on that, we assign quadrant numbers to the phase shifted data. And then we extract the maximum amplitudes at each time sample. And so what this process does is it effectively converts every data point in our seismic wiggle into an equivalent peak or trough, which allows us to utilize all samples in our analysis. So this is a significant advantage over traditional methods. We can compare how conventional seismic data works with the DQ trace. So notice how the traditional sinusoidal trace transforms into a blocked format. So this transformation allows us to see sharper boundary at layer interfaces. It's consistent, gives consistent amplitudes within the lithologic layers, and it's overall a better representation of actual geology. Over on the right-hand side in the cross-plot space, you can see how the DQ data points migrate to form distinct clusters, which make it easier for us to identify different lithologies and fluid contents. One of the coolest things about the DQ trace is its ability to mimic porosity logs, as you can see in the lower left. So this isn't just a coincidence, it's based on fundamental rock physics. Relationships between the acoustic impedance, the VP-VS ratio, and porosity. And so the DQ trace is effectively combining these relationships, providing us a really robust estimate of porosity just directly from the seismic data, which is pretty cool, I think. One of the things in seismic analysis is understanding the tuning effects. And so the DQ trace handles these in a very unique way, where we get our optimal performance between a quarter of a wavelength and half a wavelength. We can also see clear representations of thickness variations with the DQ trace, and we maintain accuracy even in thin beds. We can also look at now how the DQ trace performs across the different AVO classes. So what we've got in this slide is the class 4 bright spots, and then the class 3 traditional gas sands that we're used to in the kind of Gulf of Mexico. And so what we can notice is that the DQ trace consistently differentiates between the wet sands marked with a W and the gas sands marked with a G across both of these classes, which provides, you could also see it provides kind of a clearer visualization than conventional displays. We can also look at class 2P, the phase reversals, and class 1 where we have the high impedance sands. And we notice that the distance and quadrant method continues to provide clearer visualization into the reservoir details. Okay, so the DQ trace's power also extends to statistical analyses. And so what you can see in these histograms is that this method separates different lithologies and fluid contents more effectively than conventional data. So you can notice that we have a distinct clustering of gas sands, as well as a clear separation of wet sands. Other things you can notice is that we have systematic trends across all of the AVO classes, which really allows for good regional mapping and makes the characterization a little bit more reliable. So there's a lot more details of the workflow in our paper and interpretation, but hopefully this video has helped you see that the DQ trace method represents a good new tool in seismic interpretation to help us enhance visualization of the reservoir boundaries. It helps us improve fluid content discrimination, have more accurate thickness representation of our beds, and it has a direct correlation with porosity. And then if you do the statistical analysis, you get better separation of the lithologies. So I'll be making more videos because there's a lot more to this method than I'm saying here in these 5 minutes. But a lot of details of the first aspects are in this paper. We also have a lot of information about this method up on our website, and I'll see you next time.